Thank you so much. We are going to start the presentation, okay? Well, my name is Daniel Maroto, technical expert from Bull, and today I'm going to present a paper that we published 3 months ago. Okay, so basically about Qaptiva HPC and some quantum distribution emulators for HPC centers. Okay, so first of all, who are we? Okay, we are Bull. We are a company with more than 100 years of expertise, and the core activity is the supercomputers. We have been through a lot of transformations, merging, changes throughout the company. So we started with Bull, then we acquired Honeywell Bull, again Bull, then Atos, that maybe some of you know us with that name. Then we changed the brand name to Evident, and surprise, we came back to Bull. Okay, so I think it does work, and if in the future we change it, we will be back to the origin. So I really like this image because okay, our core activity, as I mentioned, is the supercomputers, and we are the third world supplier of supercomputer centers, and the first European one. An example of our supercomputers is the one that Thomas mentioned before, the Jupyter supercomputing, that is the 14 in the top 500 list, and the first in Europe. And the other example, I think you already know it, and some of us will visit it as, for me in this case, the first time, and it's the Mare Nostrum 5 here at the VCC. Okay, so this is our strategy because the core activity is HPC, but we also have another activities like AI, or in this case, quantum computing. So what are we doing in quantum computing is we divided our strategy that is called Qaptiva into 3 main pillars. Okay, first one is consulting and training. What we do is to talk with companies, public organizations, or even private, just to guide them through this world that for most of us, I include myself, is a completely new paradigm, in which sometimes you need help from experts to understand it and see where you can use it. That's the main goal. The second pillar is these appliances, the Qaptiva appliances, which is basically a hardware focused for quantum emulation. Okay, we can emulate qubits from 30 qubits, 40 qubits, to 100 of qubits, always depending on the paradigm of emulation. And we also have some partnership and sponsorships. So through our appliance, you can use some quantum computers, connect them through it, and use these real devices that at the end is the goal. And the third pillar, the software layer. We have developed an open source programming language, programming language, no, an emulator, that is my QLM, okay? It's open source, you can use it. There's an extended version that is under the license with more capabilities, more type of emulation, and more features. Okay, and we are also owning the Qaptiva HPC, that is the one connected with these supercomputing platforms, and that is the one that we are going to benchmark against another ones today. Okay, so anyway, we go through the results, or I will present the results of the paper, and we're going to split it into 2 parts. First, with CPU multi-node environments. Okay. Well, the benchmark was presented, or the experiments were run in this Spartan-Bull hardware, okay, with only CPUs, no GPUs, and with between 2 to 156 nodes, using 128 gigabytes of RAMs, and the maximum capacity of emulation of computation of 2.75 petaflops per second, okay, as you can see there. We benchmarked 2 emulator softwares, Qaptiva HPC versus QS. And to do the benchmark, we need some problem instances. For you who knows a little bit of quantum computing, this is the typical example of a combinatorial optimization problem that is called NISQ. Okay, NISQ problem solved with the KU algorithm, and we were able to reach the top of 40 qubits basically translating into graphs with 40 nodes. Okay, so here are the first main results. You can see in the image that we were benchmarking the number of qubits in the x-axis, and then the colors are the dashed line for QS and the solid line for Qaptiva HPC. Over there is stated like the D-line alg, okay, is the name of the state vector emulator, but it is represented the Qaptiva HPC. So what we did is, okay, let's take 2 nodes of the system, then 4 nodes, 8 nodes, until 128 nodes, okay, and here are the results. Basically, as an overall, there's a gap. Okay. I think I will take it as a sign that, like, okay, go ahead. You can see here that there's a gap in between the corresponding lines of the same color. This meaning basically Qaptiva HPC performs a little bit faster in terms of time, okay, than QS in most of the cases. And the maximum performance difference gap is with 2 nodes at the very beginning, 57% of improvement versus 128 nodes with 59. The key point here is that Qaptiva has a good resource management. So basically you are saving half of the memory. So you are matching the same performance with half of the memory, which directly leads to have this extra qubit that you can see there, that reaching 40 instead of 39, which of course is also a good number. In terms of efficiency, we also performed some experiments. This is basically to show that there's like a good core efficiency, okay, with the largest variance with 16 nodes. And we had this moderate overhead. But the picture on the right, this one is indeed for me more interesting, in the sense of it is showing you the communication to computation time. So basically how much time you are communicating with other nodes and how much time you are really performing your own computations. And you can see like at the very beginning, then you have like exponential increase, but suddenly like it started to behave like linear increase in the number of nodes, okay? And this shows you like basically the trade-off between, okay, you have more nodes, more computational power, let's say, but then it comes at the cost of communication between these nodes. Nice. So this was the benchmark for CPU emulation, okay, environments. Let's go now with the multi-GPU. If we're talking about, this was the hardware. Maybe it's familiar to you right now because of the previous presentations. And, this has these capabilities, so 175 gigabytes and 4 GPUs per node, okay? If we're talking about multi-GPU or GPUs, then obviously NVIDIA has to be there. So we extended the benchmarking, and we add CUDA-Q as another benchmark. If we extended the emulators, then okay, let's do it the same with the problem instances. And apart from the KU algorithm, we also generate some random circuits instances to measure the performance with some parameters that we can control in these circuits. Nice, but before, just a quick summary that the difference between CPU and GPU, at least in the Qaptiva HPC, we get like a 14 times faster emulation. How is it? How do we get this speed up? First of all, with let's say a software layer or more theoretical layer in which we apply some plugins, some algorithms to reduce the overhead inside quantum circuit algorithms. So we're reducing the number of communication layers and also their duration. And then we have another advantage layer that is dedicated to GPU. So we are using this architecture that is NVLink instead of the more general PCI that is plotted there. And the results are quite interesting. You get a really high speed that indeed is really needed in this quantum distribution emulation. Okay, So what we have here is basically a dash line for random circuits and a solid line for KUA test. We have in green CUDA-Q, orange for Qaptiva, and blue for QS. You can see the difference between QS and the rest is a little bit interesting and appealing, and the best performing one here is CUDA-Q. And another point to mention is that this gap between also the dash and solid lines. So we added these random circuits, and it's good for the research because it has a lot of more overhead than KUA. Okay, so on the left side of the screen we have the KUA. On the right hand we have the random circuits, and overall we have that Qaptiva HPC multi-node. Okay, we're talking about multi-node. It's faster than the rest, and because of this good management of resources, we have this extra qubit with same number of nodes. Okay, and on the other hand, if we go to the random, in this case, CUDA-Q with only one node is faster than the rest of the emulator, but if we increase the number of nodes, we add these communication layers, then Qaptiva starts to perform a little bit faster. QS remains the last one between the three of them. Okay, this is basically the same image, but here I like to highlight that indeed QS scales a little bit better, but we had to stop the benchmark only with 8 nodes, so we were not able to reach the 16 nodes. Okay, and the same with the random circuits. We perform it with 1,000 gates and measurements of such variables of 10 terms. Here, basically, we were using the NVLink architecture that we mentioned before. And as you can see there at the very bottom, CUDA-Q performs faster than both, but then the results change when we increase the number of nodes. Okay? So anyway, the conclusions, we have the time reduction of 50% with 2 nodes and 59% of 128 nodes. As I keep saying, we're using half of resources with respect to QS, so directly linked to the number of qubits you are able to emulate, with a stable core efficiency, which is also necessary for this type of computations. And finally, we have that CUDA-Q is the fastest if you are using only one GPU, and if we added more nodes with multi-GPUs, then the way it's configured inside the Qaptiva HPC make it a little slightly faster than CUDA-Q. So as a really last conclusion, we're working with quantum distribution emulation softwares. Then we should focus on this optimizing these communication layers, because it's going to reach you to better scalability and memory efficiency. So thank you so much for the attention. And if you have any question, I will be glad to answer it.
Thank you very much, Daniel. Okay.
Hello. Okay, I have 2 questions.
Yeah.
The first one is, how do you represent the state in the quantum simulator to use less resources to store the same state? And also in the benchmark, you also compare like the accuracy or the error of the different quantum simulators, or you just compare the performance?
Okay, I'm going to answer the second question first. Basically, we didn't measure the accuracy, you mean, here, because with the KU algorithm, we only run one iteration, so we didn't run the full algorithm, just to measure the performance and have a more or less way to know how it will scale, okay? So not performing the full one. And even because it depends on the problem instance, but if we reach 40 qubits, then the accuracy is based on another solution, and maybe that solution is not your optimal one. So it's harder to measure it. And regarding the first question, if you can repeat it, please.
Yeah, how do you represent the state inside the quantum simulator? Because, for example, Quest uses like 2 floats per amplitude, so it requires, I think that it's like 16 bytes per amplitude, so it's like linear. How do you do for use less resources for the same state representation in the memory?
So here is in this layer, okay, so as you can see like in the blue square, okay, then we have some optimization for the quantum algorithm, so basically transpilation techniques to reduce the number of gates. I think it was Thomas that mentioned it, that then you have your highest level of transpilation and you can reduce the number of gates at the point of you run out of gates and you don't have to perform any operation. This is one type, reducing the depth of the circuit, and there are some more patented compression algorithms that they are inside the Qaptiva and you can use, but I cannot explain it.
Okay, thank you so much.
Welcome.
Okay, I have a question.
Okay.
So you say that with GPU it's 14 times faster.
Yeah, in this case, in our, in the simulator.
In your setup, so follow this case. I'm using Qaptiva because it performs better, it's faster than the others, fantastic. How long will it take for me to access a GPU? So getting access to a GPU nowadays is not easy.
Okay, I understand.
It's not cheap.
No, not at all.
So is it worth
to access
have this 14 faster?
Yeah, indeed it does. For example, I'm working right now with quantum machine learning in my daily job. And the thing is that sometimes it's not running one circuit, you have to run the circuit 100 times, 1,000 times, and different instances, different architectures. So you are going to have a bunch of instances that you're going to run, and 14 times, it's not only, it's 14 times reduced, so instead imagine if my simulation takes 14 days, I prefer if it takes 1 day only.
So you prefer to wait in the queue longer and have it in 1 day, but at the end of the day, it's not going to take 14 days at all.
Yeah.
I'm not a quantum expert, just to start with that.
No worries.
What I might be saying is a bit stupid. But we've seen on Thomas' presentation that qubits tend to be very noisy, right? Very noisy, okay, right? Or unreliable on the results. Is Qaptiva able, or how does the Qaptiva results translate to real hardware? Right? Can you emulate this intrinsic noisiness of qubits to have a more realistic simulation?
Okay, so here, for example, we were using the state vector, which is exact. So we're using linear algebra, and there's exact, fidelity equal 1, which, as you mentioned, is unrealistic, and really unrealistic in real hardware. So here in Qaptiva HPC, there's a separated QPU that allows you to implement some noise models, which mimics you can mimic the calibration, the real calibration on some hardware vendors. You can mimic also the topology, you can mimic the connectivity, for example, the X connectivity of IBM, everything, you can model it at the cost of increased time. So this is the whole trade-off, but yeah, for sure you can do it.
We still have time for some other question. No? Okay, so thank you very much, Daniel.
Welcome. Thank you.
And if you have questions, just look
please
for
reach
him
me.
after.